this has been done in relation to a SAMP model study. I have been a part of this program also, myself personally as a consultant to WPI Limited. The owner is the Indian Power Corporation India Limited, as you see, and the consultant development consultant private limited. I have been consultant for WPIL, and one of my colleagues. It was done, this simulation for this has been done. It is not a very old project, maybe 3 years back we have done it. But then prior to this, when I personally had not made any program on the simulation of SAMP model. This is called a SAMP model, circulating water. This condenser cooling water. You know, in a power plant you require a lot of cooling water for the condensers. Usually this cooling water will be heated up during the process of cooling the steam that come out of the turbine. Yes, come out of the turbine, and it requires a lot of cooling water. So it's a vital component. The cooling water pump is a vital component in power plant operation. You can understand it's a very critical component. And after getting heated, it goes back to the cooling tower and then collects in that SAMP, and from the SAMP you have several pumps which pump in and sends it back to the condenser system. And there will be, of course, make up water, because during the process of cooling there will be some evaporation loss, and then after condensing water, cooling water, and it's required that the pumps, while pumping water from the SAMP, I will show you a physical model of the SAMP that we had carried out test for a power plant under West Bengal Power Development Corporation Limited, WPDCL. They have around 120 megawatt plant in Bakreshwar in the district of Birbhum in West Bengal. And myself and one of my classmates and colleagues, Dr. Kumar Shaha, who had also been the head of the development of Yadavpur University, was my classmate in the undergraduate class, and later on my colleague. Unfortunately died some years back. Anyway, myself and Professor Shah, we have been instrumental in conducting this model test on SAMP. I can show you the physical model of it. Can you see? This is a SAMP model. It was a 1:8 model. You know, in fluid dynamics, before this CFD and all these things came in, we had to rely on experiments. Even today, we have to finally rely on experiments. And fortunately, we have the theory of physical similarity, law of physical similarity, and principles of similitudes and dynamic similarity. You know all this. So there you have to maintain geometric similarity, you have to maintain dynamic similarity in terms of certain dimensionless numbers, which are important for a particular situation. Say for example, a flow through a closed conduit under pressure, Reynolds number you know. And then for compressible flow, Mach number similarity. It is a free surface flow, it's fluid number similarity. You know all these things. With a surface tension force which come into picture, when the scale of the object is very small, then surface tension force comes into picture, the number comes into picture. So there. And then if you have the
buoyancy, induced flow, natural convection, then Rayleigh number or Grashof number. Okay, all these things come into picture. Grashof number, of course, is independent. It's not independent. Independent is Grashof number, Reynolds number, Prandtl number, Freud number, Mach number, Weber number. So depending on the particular situation where a particular type of force is important, so inertia force is important, discuss force Reynolds number. Inertia force, gravity driven flow, open channel flow. Then you have Freud number similarity. You have to maintain when you compare between two flow situations. If the dimension numbers are the same, then you say that the flow are similar, and one can use the experimental results of one particular situation to another particular situation. Of course, the dimensionless results. The dimensional results must be then transformed into dimensional results. Say, for example, the coefficient of drag versus Reynolds number. No? When we conduct an experiment, if Reynolds number remains the same, coefficient of drag remains the same. For one experiment, I can get the particular Reynolds number to make choice and get the value of the drag, and then convert the drag value, dimensional value to CD value, coefficient of drag, and then that dimensionless curve become invariant as long as the geometry remains the same, similar. Okay. So the dimensionless number similarity has to be maintained. For open channel flow, see here, you see this is the passage of water. Okay, it comes down to chamber 1, 2, 3, 4, 5, 6 chambers. They are physically isolated. Okay, and then here you have the sump. Okay, and you see the pipelines going inside. Okay, and then you have the pump inside, which sucks in. Okay, and then distributes. Now this is a model made of perspection by two structures. Okay. Now, according to fluid similarity, you have to maintain fluid similarity based on this. Again, let me. You see. This is, can you see? This is the physical model of the exactly replicated from the design. Okay? This is the pump. This is called the suction hole. Okay? So actually, if you take a section of the sump, you have the different stages, you have some stages of filter, okay? Then you have the guide trains and all that. Right. The shaft comes down, rotates, okay. And then the here you have the motor. Like this. Okay. It's a must pump. It's a pump. Water. It has a screen. It's a must pump. The pump is that one. It's in the horizontal position up. Okay. These are static vanes. These are static vanes. You can see the vanes. They are static. These are not the impeller vanes. These are not the pump vanes. Static vanes at the inlet. This is to break the circulation. You don't allow vortex. Okay. So if you have a intermediate plates, static plates, then the vortex will be broken. Is that clear? Vortex breaker. You don't want vortex. Okay. The swirling velocity would induce air suction. Sometimes, if you start like this, some dimple, small dimple. It is called type 1. This is not dangerous. And dimples and then going off, dimples and then going off. Then bigger. Okay. And then still bigger and some air pockets. You see, this is air. There is no water here. This is a free surface, open channel. You understand that? And then this is air, and in worst case, it will simply break the suction. All air entry. And the pump will fail. So there are certain codes in Hydraulic Institute, HID, America, or BHRA, British Hydraulic Research Association, BHRA, which says what should be the submergence. If this is the floor, okay, what should be the disk clearance? What should be the, this is one section, then one after the other.